This presentation is about glacier recession across the Andes, and it's really bringing together two different outputs from two different projects, but they are related, and I'll try and explain a little bit about how they're related. I'm going to start by just saying glaciers are, I know I'm preaching to the choir here, but I just wanted to emphasize that glaciers are really, really important. There's a very substantial volume of ice in glaciers. And if all the glaciers in the world were to melt, it would be about 32 centimeters of sea level rise. Some of the areas with the most ice are Alaska, which is the number 1 circle down here, and then in Patagonia, the number 17 circle down here. And there's also glaciers in the tropics all through the Andes, and you've got glaciers in the lower 48 in the US, and quite a lot of volume of ice in Arctic Canada. And globally, all of these glaciers are shrinking. They're losing mass every year, more mass than there's being replenished in that accumulation season. And that system, that signal is coherent globally. When we look at ice loss globally, these circles show how much ice is being lost every year. And globally, it's 266 billion tons, 266 gigatons of ice every year. The blue part of the pie is marine terminating or terminating in the ocean. The white part of the pie is land terminating glaciers. And Alaska is the single biggest contributing unit. So that's using 66 billion tons of ice every year. There's also a lot of ice being lost from the southern Andes and also from the tropics and the low latitudes. Lots of ice being lost in Greenland and around the Antarctic Peninsula. And all of that ice loss together is important because it's contributing to sea level rise. Over the last 30 years, Earth has lost an enormous volume of ice, about 28 trillion tons. And that ice loss, the rate of that ice loss has risen by about 57% since the 1990s. When we look at where the ice loss has come from, it's really glaciers that are dominating that loss of land ice. These lighter blue colors here reflect floating ice that doesn't contribute to sea level rise. And these more purpley colors reflect land ice, where ice has moved from the land into the ocean and is contributing to sea level rise. And glaciers are driving about 24% of sea level rise, again with Alaska being the single largest contributing region. And it's about the same as what we're getting from Greenland and Antarctica together. So glaciers are important because they affect the global population through sea level contributions. But glaciers are important for another reason, and that's because their meltwater is significant for downstream populations. In this paper, what we attempted to do was look at where are the mountain glaciers in the world and how important are those mountain glaciers for downstream populations. The bluer the color of the hydrological catchment, the more important the glaciers are in that region for downstream populations. So we've got places in Canada and North America, and also parts of the southern Andes, where the water that's produced and stored in mountain glaciers is then used by downstream populations. And in places that are very dry, like large parts of the Andes, that water is even more important because it's a life-giving buffer against drought. This map of the Andes shows in the circles its population centers. It's where we have large concentrations of people. And the color, the yellows and the oranges, is the water stress that these regions are experiencing. So when we have glaciers in the central Andes and the northern Andes, in places like Peru and Bolivia, central Chile, and even southern Chile, the glaciers here are supporting downstream populations through irrigation, hydropower, domestic consumption, and industry. They're also providing ecosystem services, supporting biodiversity and wildlife. When these glaciers disappear, this water stress is likely to increase because the glaciers are no longer able to provide that buffering capability that buffers people against droughts. So that's the context within which we undertook this work. And I'm going to talk now about two different projects. The first project, which was published just a week ago, is looking at the acceleration of glacier mass loss for the Juneau ice field in North America. This is a nice drone photograph of the overlooking Taku D Nunatak, and that's Taku Glacier in the background, the accumulation area of Taku Glacier. Now, it's a large team, a large cast of people, all of whom were really instrumental in bringing everything together. And you can go and read the paper, it's open access. Juneau Icefield sits here in Alaska and British Columbia, straddling the boundary. And as you can see from this photograph, as I'm skiing across the ice field, and I took the photograph, and you can see it's really, really flat. This is the upper portion of Taku Glacier on the top of the ice field, and it has a surface slope of about 1 or 2 degrees. So when you're skiing across it, it's hard work. You don't get any help at all from the gradient. But it also means that it's got, unlike a mountain glacier, which has a long profile that might be quite steep in the upper parts, it has a profile that's very, very flat in that upper portion. And that's the same for a lot of the ice fields, not only in Alaska, but also around Canada and around the Greenland ice sheet, and even around the Antarctic ice sheet. There are lots of these ice fields in high latitude regions, which have this very low slope surface top area. What we attempted to do in this project was try and reconstruct a really long time series of glacier volume loss. But critically, we wanted to go back in the pre-satellite era. And there are several ways in which we can do that. One of the first ways is to map the geomorphological imprint of the glaciers in the valleys around the ice field. And you can see this geomorphological footprint really clearly in satellite imagery. So we can reconstruct things like moraines, we can reconstruct trim lines, we can reconstruct areas of scoured bedrock, and we can say, oh, we think the glacier was at this location. We also dove into the literature and found all the chronological data we can find about when the glaciers were at that neoglacial extent, of which there's quite a lot of archival evidence. There were people here in 1770 when these glaciers were at this region, and they went and mapped the ice field. They went and mapped some of the glaciers. Not all of it, because it's very inaccessible, but there are naval records of some of these glaciers. There's sea level records, and there is also things like tree ring records that tell us when the ice field was at its maximum extent, which is well documented to be about 1770 AD. And then the USGS flew over the ice field in 1948 and again in 1979, and they took a lot of overlapping aerial photographs. They flew over it just with a normal camera, downward pointing nadar camera, and there's no geospatial information associated with any of those photographs. So we had to do what we had to do is we had to stitch all of those photographs together to make one image of the whole of the ice field and a digital elevation model of the whole of the ice field. We did that using structure from motion techniques to make a 3-dimensional image of the ice field, and that allowed us to reconstruct the surface elevation of the glaciers. We've then got Landsat and Sentinel imagery from 1990 through to 2019. And we have ASTA-derived digital elevation models from 2000 to 2020. So we have digital elevation models in 1770, 48, 79, 2000, 2010, and 2020. And then we have images of the ice field at these time slices as well. So this is the Juneau ice field, and the yellow and orange colours are that low slope interconnected plateau. There's about 40 glaciers that drain down from that plateau, and then there's hundreds and hundreds of small mountain glaciers that surround all of the ice field. Most of that ice volume is concentrated in those 40 outlet glaciers. You can also see some black lines on the map. Those black lines on the ice field are where the snow line was in the year 2019, the end of summer snow line in September 2019. If we zoom in on Mendenhall Glacier and Lemon Creek Glacier, very near to the city of Juneau down here. You can see the individual reconstructions of those glaciers in each time slice. And those black dashed lines there, those are the glacier extent when it was surveyed by surveyors from Juneau. So you can see that in 1770, the glaciers were in the valley floor, and then they started to shrink back, and you've got those different time slices there coming through from each of those glaciers. When we look at the total rates of area change, there's a really significant acceleration. So from 1770 to 1948, there's a fairly steady rate of glacier recession of about 3.7 kilometers squared per annum. And where we do have historical records, they suggest that that recession was fairly steady and continued. It then slowly increased over the next 200 years, over the next 100 years. So rates of recession now are 45 kilometers squared per annum. So they're many times faster than they were just a few decades ago. If we look at it visually, this top graph here shows the change in area as a percentage for each glacier, change in area per time. And the bottom axis here is years. So we go from 1650 to 2020, and there's three estimates of glacier area change, 1650, 1770, and 1850, just to capture the potential uncertainty about the start of the Little Ice Age. And you can see a really sharp acceleration in rates of area change after 2005. This middle graph is the thinning of the ice field. So it's the average thinning, glacier averaged thinning per glacier in meters per annum. So DHDT is the change in height through time, and that's glacier area averaged. And again, we can see perhaps a slightly earlier increase, but a substantial acceleration in the last 10 years. And this bottom graph is the volume change with the uncertainties. The dashed line are if we assume an earlier or a later Little Ice Age. And you can see that we've got really three time slices: Little Ice Age to 1979, then 1979 to 2010, and then after 2010. It's actually doubled from what it was just 20 years ago. All in all, the area shrinkage is now 5 times faster than it was 40 years ago, and volume loss has doubled compared with 1979 to 2010. So this ice field, this one small ice field in Alaska alone, is losing nearly 6 kilometers cubed of ice per year. That's 5.4 billion tons of ice being lost from this ice field every year. And I wanted to put that in context. So this is an image from NASA showing what 1 gigaton of ice looks like over a city. And you can see losing 5 of them from one ice field every year is a very substantial volume of ice to lose indeed. What's happening to Juneau ice field is that the snow lines are now rising up to be onto the plateau. These snow lines, and you can see them here in this image, you've got the duller grey glacier ice, and then you've got the lighter, whiter snow. These end of summer snow lines are now reaching that plateau. Here's the end of summer snow lines, and the yellow and the orange is the plateau area. And you can see these snow lines in 2019 are now on the plateau. We map these snow lines over multiple years, and we have mass balance records from multiple years. They all show that that snow line is now consistently on the plateau. That means that we now have thinning on the plateau, and that area in which glacier thinning is occurring over a much, much bigger area. Other drivers of the acceleration and change is that the ice field now has a lower albedo. We also mapped and measured the albedo over the last 40 years. And as that snow line has been rising and the glaciers have been shrinking, the albedo has been lowering. That means that the grayer, duller glacier ice is absorbing more energy and melting faster. So this is one of several melt accelerating feedbacks that are accelerating this drive in glacier melt. The concern that we have is that this plateau ice field could be pushed past an irreversible point of no return. Because it has a low flat slope in the accumulation area, once it starts to thin, it's very difficult to stop it. If we have a temperature change through time, and we've got a change in temperature, an increase and then a stabilization, your mountain glacier may be able to stabilize and regain an equilibrium. Whereas once your ice field, your plateau ice field starts to lower, it lowers into warmer air. Once it starts to do that, there's a hysteresis. You need to make a much greater forcing in the opposite direction in order to halt it. So I think we have a very limited amount of time to stop this process before it becomes irreversible. And that's one of the great concerns, because Juneau icefield is typical of many ice masses and high latitudes across the world. This project we took some of the principles from this project and we used them in a new project, which is a NERC-funded project with a large cast of people. Some of them, Jonathan and Owen, are with us today. The PI is Jeremy Ely. And this project is called Deplete and Retreat, the Future of the Andean Water Towers. And our hypothesis was that glaciers in the Andes cover a large amount of area. These circles here are the glacier areas, the lines of the glacier length, and they go from the large Patagonian glaciers in the wet Andes right up into the tropical glaciers. And all of these glaciers are important for water resources. So we want to know how they have behaved in the past, and our plan in Deplete and Retreat is to use that data to calibrate and evaluate numerical models to make better projections of glacier behavior in the future. We recently published this work as well. This one was led by Jonathan Karavik, and we looked at mapping the glaciers across the Andes during that late Holocene neoglacial readvance and looking at how much those glaciers have changed over the last 200 years. Like in Alaska, the glaciers of the Andes have left behind a really clear geomorphological imprint. So there are large moraines. There's a good deal of geochronological data that we can use to date the timing of these moraines. And they're very, very fresh and they're very clear. So you can see we have moraines right from Peru, Caricalis in Peru at 13 degrees south, right down to Torres de Paine in southern Patagonia at 51 degrees south. So covering an enormous latitudinal gradient. There's a lot of published literature dating the age of those moraines when the glaciers were at those moraines. And all of these circles in these little maps show where that geochronology has come from. And we also undertook some field work to ground truth the mapping, to check the moraines, and also to date some of those moraines using iconometry. And we've reconstructed the change in glacier area across that large timescale. So this is comparing that last neoglacial readvance during the Little Ice Age to the year 2000, so the last Randolph Glacier inventory. And we've got our tropical Andes, our central Andes, and the wet Patagonian Andes. In panel A, the area change is in kilometers squared per annum. So the bigger the circle, the more area change there's been. And then it's in the panel B, it's the percentage of area loss. All in all, we can see that there's been a 37% reduction in glacier area, but it varies across that latitudinal transect. We then compared this rate of recession to modern rates of recession from glacier inventory data. So here we have glacier inventory data. These inventories are starting really from the year kind of the 1990s. And we can see a really steep acceleration in glacier area change across the Andes, ranging from a 12 times acceleration in Peru down to slightly lower rates of acceleration in the wet Andes in Patagonia. But the northern parts of Peru, which are the areas that are most water stressed, are the areas with the most significant acceleration in glacier recession. So both of those papers are available to read online if you want more details. But I will summarize to say that what we can see is an America's wide acceleration in glacier mass loss. And it's really by using these longer term data sets that we can understand the roles of thresholds and melt accelerating feedbacks and accelerating mass loss. The concern that we have is that future change risks passing tipping points and crossing thresholds, after which it's increasingly difficult to recover the glaciers. And going forwards, we'll be using these detailed paleoglacier reconstructions to improve our future simulations. So thank you for listening. Pam, do you want me to go straight into my website, or do you want to do a Q&A on this one first?
Yeah, let's go ahead and do a Q&A on this one first, if it's okay.
Sure.
So we'll open it up for questions. And I have sort of a jumping off question, because you talked about the Juneau ice field as a small one, and it's actually quite large looking at the scale. Would you characterize this as sort of a remnant of the Laurentian ice sheet in essence? And are there larger ones, if that's the case, that are larger than this one somewhere else in Alaska or Canada?
Yeah, I think this ice field is, I think it's about 5th or 6th in the world in terms of how big it is. It depends a little bit on how much you divide up the other ice fields, because some of them are like right next to each other.
Yeah.
But you've got those ice fields like right next to it, like the Kluane ice field, and then you've got ice fields like the northern and southern Patagonian ice fields.
Yeah.
And together they make up the largest ice fields in the world today. There are smaller mountain glaciers, but in terms of an area of interconnected glaciers with a shared accumulation area, it's one of the largest in the world.
Yeah, it sort of looks like a mini Greenland in that sense.
Yes, and I think some of the feedbacks that are accelerating melt are likely to be similar to some of the processes that we might expect to see in Greenland. So some of the things like changing albedo and surface lowering, producing kind of tipping point behavior would also be seen in places like Greenland, but on a much bigger and longer scale, because there's a lot more ice in Greenland.
Yeah, yeah. But it might be a way for people to sort of understand those thresholds, to look at these ice fields instead, because it's so similar.